Hello and welcome everyone to another Applied Flow Technology webinar. My name is Nick Vastine. I'm a business applications engineer here at Applied Flow Technology. First, I'd like to thank everyone for taking some time out of your day to learn pump concepts and particularly transient analysis. So today we're going to be running the gamut. We're going to look at a lot of different things regarding pumps in transient analysis. So we'll look at pump startups, pump trips, some different options that we have for modeling pump transient events, and then some different ways that we can initiate those transients. So there's a lot of content to get through today, so we'll jump right in. But before we get started, the first big question is, where do we start? So for context, this is the third installment in what we're calling the Pump Concepts series. So we had a few other webinars in the past. We had Back to Basics, which was really the fundamentals of pump system analysis. We looked at what makes a pump curve shape the way that it does, how do you size a pump, how do affinity laws affect the pump curve, and then finally, how do pump configurations, like pumps in series or in parallel, impact how those pumps will interact with the system. We had another webinar a few weeks ago that was focused on pumps and reliably operating them. So that focused on efficiency standards, looking at regions like the preferred operating region and the allowable operating regions. It also looked at variable frequency drives as a way to change how a pump is operating to make sure it's operating close to its best efficiency point. And then also considered things like net positive suction head. So if those are topics that you're not entirely comfortable with, we won't go into those in this webinar, but there are other resources and other previous webinars you can go back and reference, and then you can always circle back, watch the recording of this webinar, or if there's any topics we bring up here, know that there's other places to learn that in more depth. Today's webinar is focused on transient events. So in particular, we're going to be looking at pump startups and trips, and then we'll take a look at how you can model it with speed versus time or inertial modeling. The final installment of the series is coming up next month, where we'll look at reverse flow through pumps. So we'll look at how specific speed can impact how we model that reverse flow, and then finally do some 4-quadrant analysis. So if you know where to register for these webinars, obviously if you're watching live, then you can take a look at registering for our upcoming reverse flow webinar, which will happen next month. Or if you're from the future and you're watching the recording on YouTube, again, you can look elsewhere on our YouTube channel for these previous installments. And if you're far enough in the future, you can also watch that reverse flow webinar already. So go ahead, register for the live webinar if reverse flow is something you are concerned about, or you can always watch our recordings from our YouTube channel. Again, just giving some context of where we are in the context of the series, just so that way we're not starting from fundamentals every time that we're starting each of these webinars. So with that, what different topics are we going to talk about today? First, we'll address what we're considering pump transients and kind of limit the scope of what we're going to talk about to particularly pump startups and pump trip events. So we'll look at the different transient considerations for each type of event, and then we'll do some example analysis in the software. A lot of the analysis that we're going to do today is primarily conceptual. So we'll look at a very simple model with a very simple system layout. And then from those concepts, you can take them, apply them in your own system, understand what to look for where, rather than trying to teach the concepts in an overly complex system. So we'll take a look at those different considerations we want to take. What sort of things are we looking out for as we're doing the analysis? As we're also doing the analysis, we'll talk about how to model your pump transient event. Again, the big difference is between speed modeling and inertial modeling. That'll make more sense in the context of the software, and we have some good examples comparing the two. And then we'll also take a look at how we can initiate these transient events. So what's going to trigger your pump startup, or what'll trigger your trip, and then also how you can become much more complex with multiple criteria, or trip your pump, then restart it after a certain amount of time or after a criteria is met. As kind of a final aside is some other considerations when you're doing transient analysis on pumps. And in these cases, we won't go into too much depth on each of these considerations, but there are other resources that we can reference. So how do you address things like check valve slam if you have a pump that's tripping and your check valve is going to prevent that reverse flow? That's something that could be in the realm of pump transient analysis, but we won't go into too much depth here. In fact, I've actually done a webinar this year focused solely on this transient check valve analysis. Look, the same thing with pump interaction. And then finally, how can you mitigate these kind of transient water hammer issues using equipment, whether that be a relief valve, a vacuum breaker, or an air valve, or something like a gas accumulator, again, trying to smooth the transient event over to make it less drastic. So as you can see, quite a few different topics. Again, we'll start from fundamentals. What is a pump startup? What is a trip? We'll look at it in software, how we can refine how we're modeling that, and then improve what triggers that. So that way, if there's other conditions, other transient events happening in the software or in your transient analysis system, how can that initiate a pump startup or a pump trip event automatically, so you're accounting for that control logic. And then, of course, finally, those additional considerations or other things you should be thinking about that we won't go into too much depth. So first question on everyone's mind is, what are we defining as a pump transient? So there's a lot of different things that can happen in your system during a transient event that will impact a pump's operation. So if anything, you could consider most transient events a pump transient if you're defining it as a change in the pump's operating point. This could be something like a relief valve opening, where now you have an alternative flow path. It could change where that pump's operating point. You may see a higher flow rate. You could have a valve closure where you gradually close it, approaching deadhead on the pump. Or you could have something like a control valve failure, where if you have a flow control valve and that component breaks, how would your pump react to that system? So all those things could be considered pump transients, but for the scope of this particular webinar, we're going to focus on transients that are localized to the pump itself, where the pump is really the most significant transient event and kind of the initiating transient event as well. So within that, as I've already mentioned, there's really two big categories. So there's pump startups, where the pump starts up, very intuitive naming. And then there's pump trips, where the pump was running and then it trips and it's no longer running. How does it gradually go to zero and stops creating the pressure that's driving the flow in the system? So with a pump startup, it's transitioning a pump essentially from 0 speed or off to full speed. A lot of the startups that we're going to be modeling are considered uncontrolled startups. So imagine you have your motor connected to your pump and you just flip the motor on and you let it approach that steady state operating point essentially as quickly as it can. This is different from a controlled startup where you may gradually ramp up the pump, which we can also model in the software. And a lot of the different modeling approaches will be similar, and it's just knowing how your system is set up and how you're designing your system to inform which way you're going to design it. So some example cases for pump startups is normal startup operation. So you can't install a pump at steady state. You can't install a pump as it's already running. So every pump that you install will see at least one pump startup event in its life. That means that this type of analysis applies to every sort of system. Let's say you're building out your AFT Fathom model for your steady state operation. It's very easy to take that same system, bring it into AFT Impulse, model the startup event, and look at a lot of these same considerations that we'll talk about in the next slide. Some other cases is starting a booster pump for increased capacity. That could be a booster pump in series. It could be a parallel pumping station where you have variable operating points and you want to increase that capacity. How those different pumps will interact, that can also be considered in this pump transient analysis. The final case is you can have a pump startup or kind of a restart event, and that could happen after an emergency shutdown or something else like a power loss, anything that can cause a pump trip. So if a pump startup is starting up from 0 to full speed, pump trips are the other side where you have your pump in steady state. Something trips, maybe power to the motor is lost, and now that pump is no longer creating that pressure and that driving force, and so it'll go down to 0. So some example cases are kind of the flip side. So an emergency shutdown where you may see excessive pressure on the outlet of a pump, and to protect the pump and other components, you may shut down the pump, or that may be an indication that a process is over, and that could be a more normal shutdown operation toward the bottom. There could be an external loss of power. So if the grid goes down and now you're not supplying power to your motor, that's not supplying power to your pump, the pump will trip, and then any hydraulic behavior will then correct itself, approach its new steady state. You could also see component failure. So let's say there was a reliability issue with the pump that caused failure, where again, that pump is unable to create that pressure driving force, causing it to trip, potentially leading to things like reverse flow or check valve slam if you try to address it in that way. So these are the two big categories that we're going to look at in terms of what we're calling a pump transient. Again, a lot of these other considerations and how a pump's operating point will change, that can also be considered in AFT Impulse, but we won't address those cases specifically in this webinar. Here we're going to be focusing on pump startups, and then we're going to focus on pump trips. So what do we want to consider when we're analyzing a pump startup, for example? We can think of pump startups as a high pressure surge event where the main concern is a sudden increase in pressure. Let's imagine that we have this system, again, very simple conceptual example, where we're pumping from a lower reservoir, we have to overcome all of this static head, and we're using this pump to do it. So when this pump starts up, during normal operation, you have to see higher pressure at the pump to drive flow towards the upper reservoir, which means as it starts up, that positive pressure wave, that sudden increase in pressure can travel through the system, can reflect similar to other high pressure phenomenon. The most common high pressure phenomenon, of course, is a valve closure, where you see that sudden pressure rise as flow comes to a stop, and you'll see that same water hammer sequence in how flow and pressure interacts, again, similarly in a pump startup event. So what sort of different things should we consider when we're doing that? Or when we're doing this type of analysis? The first thing is, since it is a sudden increase in pressure, is what is the peak pressure that you're going to see? Again, you're comparing peak pressure against the design pressure of your pipes. Make sure it's not exceeded at any point, or if it is exceeded, if it's within some allowable tolerance. And then also you want to see the system response. So here we have our very simple conceptual example with two pipes, but you can imagine if you have a cooling water system with a bunch of control valves and maybe a bunch of T's and dead ends where the pressure wave can transmit throughout the system and cause reflections. That's where a tool like AFT Impulse comes in handy, because it's balancing all of those reflections and all of those pressure waves, that constructive and deconstructive interference for you, giving you the most accurate results of what your true peak pressure will be. So we'll take a look at how to do this analysis in software, but let's look at some of the other considerations we can be aware of as we're doing that analysis. The next point is pump suction cavitation. So if we imagine we're doing a startup event where all of the fluid in this system is stagnant. The pump is off. Let's say we have a check valve to prevent reverse flow from this upper reservoir to this lower reservoir. So all the fluid in this system is static. When we suddenly start this pump up, what we're going to see is a sudden creation of flow rate. As this flow increases at the pump suction, because it's at a fixed pressure or a fixed stagnation pressure, which is kind of total energy of the fluid at that point, some of that will be converted to kinetic energy, which means a decrease in static pressure. So if we, again, think about stagnation pressure in terms of dynamic pressure or energy in the form of flow, and static pressure, energy in the form of pressure, those things always have to balance. And so your static pressure can decrease suddenly when all of that energy is converted to kinetic energy, and it could drop so low that it could cavitate at that point. It could cavitate within the pipe. It could reduce to such a point where it no longer meets that net positive suction head requirement, and it could cavitate inside of the pump. But again, something to be concerned with is we think about the high pressure generated downstream of the pump, but it'll also cause a localized low pressure at this point, which will similarly travel upstream until that can balance out and approach a new steady state. So we'll see how we can examine this phenomenon as well in the software, and then we'll actually have a case where we do cause cavitation at that point. Another consideration is, how do you account for transient friction? So if we're looking at our system, again, it's completely stagnant, there's no flow. In that case, there's no friction, right? So if we suddenly start this pump up and we're saying the friction in these pipes is constant, then no friction, there's going to be very high flow. And when it settles on a steady state, that could be very different from the actual steady state where you are considering how that friction has developed. So this is done automatically for you in AFT Impulse. You won't have to change any specific settings. It will account for that time varying friction for you. One other consideration is if you were filling a pipe though. So here in this case, flow naturally wants to go in reverse. We would have a check valve here where this line would be full of liquid. You can imagine another case where this line would naturally drain out. Let's say you had an upper reservoir here, and then you're pumping to a lower reservoir, where when this pump is shut off, it could drain the whole line out. That is going to have implications on that friction effect again, because when it's completely empty, there's no friction, or essentially no friction, pushing all of that vapor out. And that is something that AFT Impulse cannot model at this point. So that's an important consideration, especially if you're doing a pump startup for something like a sprinkler system, where it may start empty and it may see many or way less losses than a liquid full system. So it's kind of an assumption that's going into it. One, account for the transient friction, because the amount of flow going through the system is going to be changing significantly. AFT Impulse will do that for you automatically, but also know that filling the pipe is one of the limitations of AFT Impulse. It's always going to assume that the liquid is, or the pipe is liquid full, and that's going to be consistent throughout the entire transient event. There's potential for entrained air when you have a pump startup. So this is especially important when you have a pump restart. So you can imagine if you have a high point in your system where as the pump shuts down, it could pull a vacuum at a high point, that could entrain air. And when you start that pump up, it's going to have to expel a lot of that air before it can generate the flow that it needs to. So because of that potential, that's also important to consider, especially when you're doing a pump restart event where the pump trip can entrain all that air. It can pull the vacuum, suck the air in. Then when you restart the pump, it has to blow all that air out before it can create the flow and meet the requirements that it needs to. So we won't have an example for the entrained air, and vacuum breakers and air valves are kind of a much more complex topic, especially if we're looking at kind of fundamentals of pump transient analysis. But again, something that you want to consider as you're taking a look in your own systems. Finally is pipe forces. So anytime that there's a high pressure event and you see significant changes in pressure, you want to make sure that the pipes are properly supported and can support that transient event as well. A lot of the time it'll just be static analysis, but AFT Impulse can also generate the pipe forces for you to bring into a pipe stress analysis tool, whether that be Caesar or AutoPipe. And from there, it can determine the stresses, check against the supports that you have designed, and make sure that it's going to be properly supported for those transient events. So as you can see, there's quite a different range of things that you can consider. Some focused on the high pressure side, where you're looking primarily downstream. Some on the low pressure side, so the sudden creation of flow causes the change in energy, dropping the static pressure in this line, potentially enough to cavitate either in the line itself or at the pump. Transient friction, which is important in transient analysis in most cases anyway, anytime that your flow rate is going to change significantly. And then also the potential for entrained air and the pipe forces, which are much more of an aside in this case, and we won't look at analyzing these cases in particular. So with that in mind, let's actually analyze a pump startup and let's see how I would approach it and kind of the different areas that I would look at. Then you can take these same concepts, these same processes, apply them to your own system, and hopefully have a better understanding of what's happening during your pump startup event. So here I have a pre-built example model where I've already built out a lot of the different scenarios that I want to look at. So within the scenario manager, I have my pump startups grouped up. In this case, we'll look at a speed startup first, and then we'll take a look at how that's different from an inertia startup. And then once we take a look at the pump trips, we'll look at how we can intentionally cavitate the system. Again, for example's sake, to see what cavitation looks like. What happens if we apply check valve slam to it? What if we add an accumulator or use some equipment to mitigate a surge event? And then we can also get much more complex a little later in the webinar. So this is a bit of a preview of some of the other topics that we'll take a look at. For now, we're just going to focus on this pump startup event where we've defined it in terms of speed. So here we have our lower reservoir where we have 10 feet of hydraulic head at this point, and then we're pumping up a hill up to 100 feet. Within the pump, what we have defined is our typical pump curve. Here we have some 4-quadrant curve specified. This is going to be covered in much more detail in that next webinar that's solely focused on reverse flow, so we won't go into too much detail here. But this is just accounting for how that reverse flow would create a loss through this pump as it naturally wants to go and see reverse flow. In this case, we won't have to worry about that reverse flow as much because we're modeling a check valve within our pump. So to stop that reverse flow, we're going to have all of this fluid stagnant to begin with. Then when it starts up, it'll overcome that and generate that flow that we want. Our transient event in this case is determined by speed versus time. So here we're just saying that in the course of 2 seconds, we're starting from the pump off and it's going to 100% speed. This could be a representation of a controlled startup. So let's say that you have a controller and you can gradually ramp up the speed of your pump like this. This could be a good way to represent that, where you can also increase the amount of time, run that as some different scenarios and see how that would change your transient response as well. So a lot of the time in hydraulic analysis, and especially in our AFT tools, is using things like scenarios to do sensitivity analysis, again, give you better insight into what's going on in your system, understanding the cause and effect. So in this case, we're starting our transient event at time 0. It'll gradually ramp up, and then it'll stay at that 100% speed where we should see it approach a new steady state. So I've already run the model, and this is when we can start looking at the output and really doing the analysis. So if we run the model again, just for proof of the pudding, right, show the full process. Usually the first thing that I would do is go to the graph results. So in transient analysis, there's a lot of information to take in because you have all of these different time steps. Again, you're looking at 0.004 seconds per time step for 30 seconds. That's a lot of data points across all of these different pipes. So graph results is going to provide you kind of the highest density of information and make it the most easy to interpret. So if we go to graph results, the first thing that I'm interested in looking at is what's going on at the pump itself. So here I like to kind of leave an image so I have a good understanding of how it's interacting within the system. Again, it's pretty convenient that our system is so simple, makes the analysis much easier. Here, if I want to look at what's going on in the pump within graph results, I can go to transient junction, I can select the pump, and now I can start adding different parameters that I want to look at. So pump speed, if we look at the pump speed, we see how it ramps up in the 2 seconds that we've specified, and then it stays at that 100% the whole time. We can look at how the flow rate will develop. So if we add a parameter, then we can go to the flow rate. And here we can see how it gradually ramps up and then approaches that new steady state. So here we can show how they're interacting across the same time axis on the X and then independent Y axes to represent the 2 different variables. Another thing that we can add is our pressures. So we can take a look at how the inlet pressure, we'll look at the static pressure, and then we'll also look at the static pressure at the inlet and at the outlet. So again, based on our expectations, we expect the inlet pressure to suddenly decrease because as flow starts generating, that'll drop the pressure at this point. And then as the pump starts creating pressure, we expect a gradual increase in pressure downstream. It's always a good idea to think about the system and have engineering expectations. So that way you're not just pulling up results and trying to explain them, you have at least an idea and an expectation of what's supposed to be happening. So here we'll add those variables again. We'll add the static inlet and then the static outlet. And what I'm going to do here is I'm going to graph both things on a single graph. And that lets us show this interaction. So here on the right, we see 100 for the outlet. So we'll change the scale to 100 as well. We'll change the major value to 20. So now within a few seconds, now we have a very simple picture of our pump startup event. We can see how the outlet pressure gradually increases. As that pressure increases, we see how the volumetric flow rate starts to develop, where now we have that driving force from this pressure to this upper reservoir, and that's what's causing our flow rate. We can also see how our static inlet pressure does decrease, again, which is what we expected. As it starts at this fixed pressure and flow starts developing, that kinetic energy has to come from somewhere, and in this case, it's coming from the static pressure component. So this is really useful, and we'll come back to this same graph format. So now what we can do is we can add this graph to the list. We'll call it pump analysis 2. So as you can see, I made a pump analysis 1 before. And now what we can do is on all of our other scenarios, as we look at our inertial startup and our pump trips, we can again see how the speed of the pump changes, how that volumetric flow rate through the pump changes, and then how the pressure, which is ultimately the driving force for flow and everything that's informed, or that informs the hydraulic solution, how those change over time as well. Some other things that we can kind of show off is, again, focusing on transient analysis concepts, is we can see how there's also this oscillating pattern. What that is that pressure wave that's transmitting and bouncing back and forth through these different reservoirs. So here we have the pump, it'll cause that high pressure will travel to the reservoir, it'll then travel back, and then we can see how that gradually dampens out until it reaches that new steady state. Another way that we can show that is with a profile graph. So this is, again, another place where I do the majority of transient analysis just because it's so convenient. Here we're going to look at how variables change over time along the length of the pipe. So here, instead of looking at a single point over time, we'll look at how all of these different points change over time. So in our profile graph, we'll say I want to select the whole system. If your system's more complex, you would just highlight the flow path that you want to focus on. Here we're going to animate the results. So to do that, you can update transient analysis, and then that will show the all of the output for all of the different pipe sets. Let's actually show that real quick. So here we have that profile graph where, again, we're showing the length of the pipe. And in this case, it's showing the maximum and minimum pressures that we see. So if our main concern was, is our maximum pressure exceeded during this transient event? This is a very easy way to see it. And you can also see where within the pipe it could occur. So imagine if this pipe was more complex, it had high points, it had low points, that would be captured in this profile graph to show where the pressure is varying. We can go a step even further and animate it, which is one of my favorite things. So now if we generate it, you can see how we have our initial static pressure point. Here we're at time 0. So if we press play, and let's actually recombine this so we can see a bit more. If we press play, we can see how over the first second, we can see how the pressure starts to increase as that pump starts up and it starts developing that flow. We can see how that pressure wave travels through the system and then bounces back. And again, this is much more valuable when you see branching systems and interaction between pressure waves, because you can see how the actual pressure and flow is related. We can do the same thing with our previous graph where we can add other variables. So we can add the velocity. And so here what we expect to see is that gradual development of flow rate as the pump starts up. So here we can do that same animation. You can see how as the pump starts, we can see how flow starts to develop through the system. So this could be valuable, again, if you're interested in the rate at which things are happening. Let's say you have a different design criteria that your pump must start up within a certain rate. So for example, a fire system where it has to meet that particular criteria within a certain amount of time, then you can do that same similar analysis using AFT impulse. So it's pretty simple, pretty fundamental. I generally look at the pump itself, and I look at how the pressure is changing at the pump, how the flow rate is changing, and then if the speed is changing how I expect it to. And then you can also use profile animations to get a better understanding of how those things interact as they move through the system. Again, no component exists in isolation. Any change you're going to make to the pump or to a downstream valve or a control valve, opening a relief valve, all of those changes to the system will inherently change how the pump is operating, the same way that any change to how the pump is operating will impact the flow rate and the pressures of the system. So in its most basic form, that's kind of the fundamentals of analysis. We have the pump analysis, speed, flow rate, static pressure, and then profile animations to see how those things travel through the system itself. All right. So if we go back to our slides again, do kind of a review of the different things that we considered. We looked at the peak pressure and the system response, so we could see how that pressure ramped up and how it developed that flow rate. We saw how the pump suction did decrease at this point, not to the point of cavitation in this particular model, but you can see how the faster that your pump ramps up, the more aggressive you're changing that flow rate, the more likely it is to drop the pressure significantly and potentially cavitate at the pump or within the pipe. Transient friction, again, this is accounted for automatically by impulse, and a good check is comparing your final steady state that the pump operates at to your normal steady state analysis. So if you look at this volumetric flow rate, which we'll say is 340 gallons per minute, and then you run your system in steady state and it's not 340 gallons per minute, that can also be an indication that something's going wrong and you may have to change some other inputs to your model. Finally, potential for entrained error, which again, we won't go into in this particular webinar, and then pipe forces, which you could consider by adding force sets to the different pipes. So that's fundamentals of pump startups. We can do similar analysis when we're doing pump trips, but we're going to be anticipating a different event or anticipating a different response. So while pump startups are what I consider a high pressure surge event, pump trips are a low pressure surge event, where the main concern is a sudden decrease in pressure. When we shut this pump off, this is what's causing all the pressure to generate flow to overcome this elevation gain and then all the frictional losses to this reservoir. So when you suddenly take that away, now you're going to see that low pressure wave transmit through the system and see potentially reverse flow. So the first main concern would be sustained reverse flow. This depends largely on your system. If you're pumping at a pipeline and it's primarily flat, for example, you may not have a large driving force for reverse flow. But in some cases, like we have here, where you're pumping up a hill, or like the previous case where it's going from that lower to upper reservoir, again, when you remove the pump, when you trip it, it's no longer adding energy. You would see reverse flow from that upper reservoir back down to this lower reservoir. If you address that reverse flow with a improperly sized check valve, then that can lead to check valve slam. So check valve slam, imagine you see reverse flow, it allows some reverse flow through the valve, and then when it suddenly closes, that's sort of like slamming a normal valve closed. That causes a high pressure spike. Again, kind of a secondary effect of this pump trip event, and we will look at how check valve slam can occur and how that might impact your results during your analysis. You can see cavitation at high points. So imagine you have a, again, high pressure pump here where it's pumping, and it has sufficient pressure at this point not to cavitate during normal operation. All of a sudden, if you drop this pump pressure, as that transmits through the system, you're going to lose significantly more pressure at this point, and that'll cause potentially cavitation, or it could pull a vacuum on the system. So there's also the potential for vacuum, which could happen before or after cavitation. Again, that depends largely on what fluid that you're pumping through your pipes. And in that case, you could use something like an air valve or a vacuum breaker valve, which would break the vacuum, again, avoid collapse from the atmospheric pressure on the outside of the pipes being higher than the low pressure on the inside, where you may entrain air, restart this pump. Now you have to pump all that air out of the system before it can generate the flow that you require. Finally, again, pipe forces. So anytime that there are pressure swings, anytime you're doing transient analysis, you can also address pipe forces. And this largely depends on the magnitude of the pressure change as well as how quickly it moves through the system. So let's take a look at doing a pump trip in the software. And again, let's look for a few of these things. So we'll look at sustained reverse flow. We'll see what happens when we add a check valve that's not properly sized. Will cause cavitation at a high point. And then again, these two, because they're much more complex, we won't cover them, but something that you should be considering as you look at your own systems. So here we're going to update these graphs. Actually, we won't update them, and we'll just come back and reference them when we go and run our other scenarios. So now we're going to look at pump trips. where again, now our expectations for what's going to happen in the system is very different. Now we have high pressure at the pump. We're going to suddenly remove that, and we can see the natural driving force is going to go in reverse. In this case, we don't have that combined check valve, so we're going to allow reverse flow through this pump. And then that will approach its own new steady state. Then we'll compare to what happens when we add that check valve and let it slam closed. So we already have our output, where here in output, it's also very easy to look at your maximum and minimum pressures. Here we can see that we do pull a vacuum at a certain point, so that could be a concern. And then the maximum pressure, less likely to be a concern in this pump trip event because it's not causing that high pressure wave to transmit through the system. It's just suddenly removing it instead. Because we saved that graph from before, we can double click it. And now we can see how instead of that smooth pump speed ramp that we had before, we see we're starting at 100% and then it'll gradually decrease. And then we can see how that volumetric flow rate also falls off, goes past zero, and in turn reaches that reverse flow point. On the pressure side, now we're seeing how the outlet pressure was higher than the inlet pressure. This is how much head was added by the pump during normal operation. Then when you trip it, you're removing that driving force. You see that reverse and that sudden decrease in the outlet pressure. Then you can see how the outlet pressure is still higher than the inlet pressure, and that's because flow is in reverse, and now the valve is, or the pump rather, is causing a loss against it. And you can see how the pump is actually rotating in reverse at this point. So again, reverse flow is a much more complex topic. Again, it warrants its own webinar for a reason, so we won't get into too much analysis of this part. But again, having the expectation of what's going to happen when you trip this pump, how can you confirm that that's the behavior that you're seeing? Or if you don't see that behavior, how do you troubleshoot and try to analyze the system to determine why? So pump speed decrease, volumetric flow rate should decrease. If we're not addressing it with a check valve, reverse flow is definitely possible in this system. And then we can see how the pressures deviate as well. A lot of the same analysis, and then we can do the same thing with the profile animation. In this case, what I've done here is I've graphed hydraulic grade line instead of static pressure. The reason I'm doing that is because the elevation of the system goes up like this. So if we look at the static pressure, that won't tell the whole story of what's actually driving flow. So in this case, HGL accounts for both the elevation and those static pressure effects. And so we'll see much more easily when that reverse flow occurs. And then we can see how that driving force is shifted to cause reverse flow. So if we play our animation, again, we'll increase the speed a little bit. We'll slow it down a little bit. So when we hit play, we can see how the pump trips immediately. We can see how the volumetric flow rate starts to decrease. Again, because it's no longer driven by that positive HGL here, where we don't have high pressure or high elevation driving flow down to this point. So as it plays out, it'll gradually settle. Again, you see the pressure wave reflections reminiscent of the water hammer sequence. Here we can see where the flow is still gradually decreasing. And now we see where that reverse flow occurs, where it's approaching that new steady state, flowing from the high upper reservoir down to the lower reservoir. If we draw out the whole animation, again, we can see how it should approach that new steady state value. So again, similar approach, visualize what's occurring at the pump, focusing on things like speed, the change in volumetric flow rate, and how the pressure at the inlet and the outlet is changing. And then you can use profile animations to get better insight into the remaining driving force that's surrounding the system. So now let's see what happens if we instead put a check valve on the system. So now we're going to try to prevent that reverse flow, but we're still going to allow a pretty significant amount. So here I'm adding the model combined check valve and pump. We're adding a check valve here, and we're allowing some reverse flow before the check valve suddenly slams closed. So again, we can go to our graph results and we can look at that pump analysis, where here we see that same gradual decrease in the pump speed. And we can see how the volumetric flow rate decreases. But then when it reaches this point right here, that's where the check valve closes and you see this very intense pressure peak. Another good thing to do is use this crosshair, and that shows across all three graphs how things are related over time. So when that check valve closes, it suddenly sets it to 0. That's what's causing this sudden increase in pressure. Here we can see the axes actually increased to 400. So let's change this to 400 as well. And now we can see how significant that pressure spike is from that check valve slam. Where again, this may be your new concern with your pressure analysis. Say, hey, maybe this 256 PSI pressure exceeds those design limits. How can we address that? Either by tripping the pump slower or changing what check valve that you're using. And then again, here we actually see some cavitation occurring as well. So knowing what to look for, knowing where to look, again, anticipate what's going to happen in your system and then see if the model itself is going to replicate that. And then when it doesn't, do your best to understand why it's not doing that. Great. The other thing I wanted to show was intentional cavitation. So this is another case where it's the same pipe, but I've changed the profile of the pipe. I can do that from the optional tab of the pipe and use intermediate pipe elevations. So now I just have one pipe instead of connecting them with branches or something similar. And here I can see how I've added this high point, where during steady state operation, that's going to be your lowest pressure point. Again, we already have results. So when we do our pump analysis, you can see it follows the same pump speed as before, where it does see reverse flow. And here we do see that reverse flow as well. And then that pressure is very similar to what we saw before. But now when we look at the profile animation, we can see some kind of more interesting results. So when we hit play, we can see how now there's a point here where it's essentially fixed at this HGL. Before, you might remember, we had this point here, and it would gradually decrease to this point and cause the flow rate to drop. We can also see that we're no longer maintaining this volumetric mass continuity. So we have zero flow in these pipes. And because it's all connected here, we're still maintaining this high flow rate here. You might be saying, well, impulse is terrible. Why is it doing this? And that's because we're not looking at the full picture. If we go to output, which is usually where you should start, you should check for warnings and things like that. We can see this critical warning where these pipes have vapor volumes in computing stations greater than 100% of the liquid computing volume. So here we can see in these stations, it's cavitating a lot. It's causing a lot of vapor volume. So much so that it's calling the whole results of your model into question. So this is an important thing to try to consider and try to remedy before moving forward. So if we look at the same profile graph, we can add another variable, which is vapor volume. Here we'll include the maximum. And then we can see approximately where that high point is. That's where all of that vapor is going to form. So as we play it through, we'll go slightly faster. Here we can see that as this vapor volume starts to increase, that's what's maintaining this flow rate here. So in essence, it's still drawing fluid and the vapor expands to fill that pocket as quickly as it can. So this isn't a sustainable operating point. In reality, what could happen is the vapor volume could continue to grow until it breaches a pipe and then kind of drains everything out. You can think of it like putting your finger on top of a straw, and that's why the liquid doesn't drain out, is because you're creating a fixed pressure at the top where it wants to drain further, but the fluid could cavitate at that point, right? So as it goes longer and longer through the animation, again, we're at 10 seconds now, you see that vapor volume continue to increase, where the system's almost approached a new steady state. But in reality, in the physical system, this is pretty unsustainable. So another thing to consider as you're doing this analysis is look for high points like this. Here there was some cavitation collapse that caused a pressure spike to transmit through the system and introduce some noise. And here we can see through the entire simulation, the vapor volume just continues to increase further and further. So just a good example from a logical standpoint, from a physical standpoint, considering the system. If you remove this driving force, what the fluid wants to do is it wants to drain out this way, but it can't do that because there's not enough supply flow on this side. So instead what happens is the pressure drops at this point, it'll cavitate, and then that'll continue supplying this flow rate because it wants to continue draining. Again, critical warning, don't ignore warning messages. Be sure to read them, work your way through them. So we're running a little short on time, but there's also an example with an accumulator where you can add an accumulator at this point. We'll do a quick example where we'll compare pump analysis, and we'll show multi-scenario in this case. So what we'll do is we'll show with the accumulator and without the accumulator. And if we generate that same graph, we can see how the pump speed trips pretty similarly, but with and without the accumulator, you get a very different volumetric flow rate response. And then you also get a very different pressure response as well. So it just shows how using something like equipment can also be used to mitigate a surge event, and also something to consider as you're modeling your system. If you do have an accumulator, you should be accounting for that because it'll impact your transient results. So short aside, again, you can have a whole webinar on a lot of these different topics, like accumulators, like vacuum breakers, like reverse flow. So keep an eye out for future webinars where we'll try to tackle these topics as well. So that's a lot of the pump trip analysis. Again, have an expectation of what you think is going to happen. If there's natural driving force for reverse flow and you're removing the driving force for forward flow, there's nothing that overcomes that. That can lead to sustained reverse flow. We can see how that can cause a check valve to slam. If there's high points in your model, it can certainly cavitate at that point. And then you can use other equipment like an accumulator to try to mitigate that. And look at that, those are all the points that I wanted to hit. So we hit sustained reverse flow, we saw check valve slam, we caused cavitation at the high point, and then again, these two are a bit more complex to cover in this kind of introductory webinar. So let's model different pump transients, so speed modeling versus inertial modeling. So speed versus time, the user is defining the rate at which the pump is tripping or starting up. This can be a good first approximation of a pump transient if you know it'll happen within 2 seconds, or if you have a controlled startup where you can actually control the speed at which the pump is operating. That's different from inertia modeling, where instead AFT impulse can determine how that pump is going to occur based on things like the pump's total rotating inertia. That accounts for the pump, the motor, and the fluid within it, the motor or driver torque, and then also the shaft speed. So in our examples, you can see here was a pump trip with inertia, where if we look at the pump speed, at no point did we define this speed curve. Instead, within the pump, you can just define this total rotating inertia, and then the software would be able to determine how quickly that pump can trip and determine this speed versus time curve for itself. So maybe a bit more accurate than just saying, well, it'll trip in half a second, which could be more or less conservative depending on the type of analysis that you're doing. You can do the same thing for startups where you can specify the total rotating inertia, and then you'll also need to specify the torque information where you'll have the shaft speed and the motor torque, and that can inform how quickly this pump will start up. So some of the concepts with inertia modeling, it's kind of one of the more complex topics, is it does require some additional information. So it'll require things like the head curve, the power curves, inertial data, so things like the rated pump speed, and then that total rotating inertia, a starting event, transient data, and then special conditions. A lot of these you should already have if you're modeling a physical system, but some things you may also need to estimate. So for example, total rotating inertia, that could be challenging to determine because it depends on the pump, depends on the motor, and the liquid that you're pumping. But it can be estimated based on things like the pump curve efficiency. That'll determine the best efficiency point, and then the rated pump speed. And from that, you can generate these relationships, which was determined from experimental correlation. So this comes from Thorley. If you've spent a significant amount of time with transient analysis, Thorley's name comes up quite a bit. And so he took a bunch of collected data points, a bunch of inertia for the pump and the motor, and then he made this curve fit based on the power and the speed of the pump to determine these inertia terms. So this can be estimated for you in impulse, but recognize that there's some pretty significant deviation where the actual value of inertia can be anywhere from plus 100% to minus 50% from this predicted value. So another opportunity to do that sensitivity analysis. Torque balance. So how does the torque element of inertia modeling work? This is why you need to specify a motor curve when you're doing a inertia setup or startup, is because you're comparing what torque is added by the motor compared to the torque required by the pump. So the transient implies change over time, so you'll see acceleration of those components when there's an imbalance. This is captured by balancing the different torque elements that are operating on the pump itself. So you'll have shaft torque, that's the difference between the driver, or the motor in this case, and the torque required by the pump. So over here, you have a lot of driving force. It decreases a little bit. You have the most driving force between the motor and the pump. And then sort of like a pump system curve where they intersect, the motor is supplying the exact amount of torque that the pump requires. At steady state, all those things are going to balance. Again, that's where that intersection point occurs, and that's where constant speed operation happens, again, achieving that steady state operating point. When you have a trip event, the driver torque drops to 0, so you're no longer supplying torque from the motor, so then the pump curve just kind of decreases until it reaches its own new operating point. The last thing I wanted to touch on is the initiation of transient events. So we'll move a little bit more quickly through this part. I know we're getting close to the end of the webinar. So there's a few different ways to initiate a transient event. The most common one is going to be time. This is like the first case that we looked at, where we can specify the transient in terms of how long it takes. So we'll have a pump startup in 2 seconds, and then it'll stay at that steady state operating point. You can also have event transients. So what this does is it'll look for this criteria to be met, essentially creating an if this, then do this situation. So there's all sorts of different event types. There's what's the static pressure at this pipe. If it exceeds this value, then do this event, then start the pump up or trip the pump. And there's all these different variables that you can explore, like velocity in the pipe, static pressure difference across the junction. If it's exceeding a pressure head, for example, then you can do that. So trigger a startup or trigger a trip event based on an event criteria, and this can be useful when you're modeling different control systems. There's also a dual event. So dual event is you're specifying 2 different criteria and 2 corresponding events. In the case of pump transients, that's going to be a trip event, and then a restart, or maybe a startup and then a trip. So if you look at speed versus time, you'll have 2 different criteria, 2 different events. If you have a startup, you'll have your start event and then a trip event. And then with a trip, you'll first initiate your trip event and then have a restart. These come in both sequential options. So in this case, you would just specify 2 events you expect to happen in sequence, or you can have a cyclic check. So it'll check both criteria at the same time. And then if either of those criteria is met, then it'll do the corresponding event. So this can lead to cycle. So let's say you trip it, and then when you restart it, that again causes the criteria to trip again. And so it can cyclically restart over and over, which could happen in your physical system. Again, it all depends on the inputs to the model. The final thing is much more complex. So let's say you have a pump that can trip due to a number of different criteria. So for example, you might see overpressure at the suction, overpressure at the discharge, insufficient pressure at either, or if you need to meet a minimum flow rate and that's no longer achieved, then you should trip the pump. This is from a multi-condition event specification. And so what that lets you do is you can use a single event and it can check for all these different criteria, where if any of them are met, then it'll trip the pump and have it do what you need it to do. So again, trying to capture much more complex control systems where you're not specifying that the pump can trip, it can trip as a result of something else that you're modeling in your system, like a valve closure or like a relief valve opening event. So you can build out elaborate and not or logic. You can build out simple events and then use those events within these events, and can get pretty complex. So it's pretty sweet. Again, if you have a complex control system and all these different things could trip your pump, this is an easy way to consider all of those things at the same time. It's useful when it's unclear what combination of events could lead to a transient trigger. Again, let the software determine if it's going to trip instead of watching each event, figuring out if it would be met, and then trying to time it accordingly. Some additional considerations. Check valve modeling. So how much check valve slam occurs depends on how you're modeling that check valve. I would consider watching a previous webinar I did this year called Check Before You Wreck Transient Check Valve Modeling. That'll be much more comprehensive in terms of what to consider. Again, much more tangential to the pump transient, but it is an additional consideration that you should be looking at as you're looking at pump trip events. Multiple pumps in parallel. So if you imagine having multiple pumps and one of them trips, that's something that you can model in the software as well. That's going to have similar high potential for reverse flow. If you imagine that all the other pumps are still generating all that pressure, now you have high pressure downstream of the pump, it's off and it wants to flow upstream to that lower pressure. So that can cause reverse flow, leading to similar things like check valve slam, and then can also lead to damaging pressure swings at the component itself. You can also address issues with equipment. So we've mentioned vacuum breakers throughout the webinar, even though we didn't add them to our model. So if you have a low pressure surge event, that could be one approach to avoid collapse of your pipes. Then it's also important to consider how that entrained air is going to be expelled on the restart, where that can also be a secondary transient event, similar to that check valve slam, where all of a sudden that valve is open, it's clearing out all the air, it slams closed, and all of a sudden you have a super high pressure spike in your system. We looked at gas accumulators a little bit. That can help smooth startup and trip events. So you can properly size a gas accumulator. That can help slow a trip event, make the pressure change much more gradual. Finally, sustained reverse flow. We'll leave you with a teaser for the next webinar. So if you're interested in how that works and how you can consider that in your own model, again, we'll cover that in much more depth later. So we made it through a lot of the content. Let's take a look at a summary of everything we talked about. So the first point is there's different considerations when you're looking at a pump startup, which is primarily a high pressure event, and then a pump trip, which is a low pressure event. In this case, it's convenient to look at both. So you can look at the high pressure, then the low pressure, again, exploring scenarios and doing sensitivity all within your single model. Again, it's important to set the expectation of what you think is going to happen, then look at the results and see if it matches, and if not, why is it deviating? Pump transient events can be modeled either as speed or inertia. That all depends on the information that you have available. And it can also depend on if you're doing a controlled startup or an uncontrolled startup. There are plenty of options and criteria to trigger a pump transient event. And then you can also capture more complex conditions such as restarts. So you can trip the pump, it can entrain a bunch of air through a vacuum breaker, then you can see what happens when it ultimately restarts. Or if you have a more complex control system, again, you can use something like multi-condition events to check for all of those things all at the same time. Finally, in addition to the pump transient itself, you want to consider other problems that can happen from a transient. So that could be check valve slam, and then you also want to look at all the different ways that you can mitigate that. You can change how the pump transient itself is occurring, whether it could trip slower or faster, or you can use equipment like a vacuum breaker, like a relief valve, or something like a gas accumulator that can help smooth those transient events over, making it less drastic of an impact. I know this can be a lot of information, so here's a lot of other resources you can reference, and credit where credit is due. A lot of these are what informed the content of this webinar. So Scott Lang, he's one of our engineering developers, so he's the one actually writing the program at this point. And so before that, he was an applications engineer who would write content for us. So modeling inertial pump startups, where to start with pump startups. If you're more interested in the transient event logic, then you can look at when to begin or and not or, trying to use much more complex logic there. And all of these tips and tricks blogs are found on our website under that Learning Center link at the top. There's also some good articles within the AFT Impulse help file. So this goes into much more detail of the theory and of the math. So looking at inertial models, detailed theory, and then startup with inertia. And we also have plenty of examples that work through the same type of analysis, which can be useful when you're building a model to have a reference point, know if the output that you're looking at is correct. Finally, with the webinars, as I've mentioned before, and we'll do a final plug towards the end, is looking at the other pump series webinars. So if you're jumping into the middle of the series and you want a refresher on things like reliability or back to basics, or if you want to sign up for the next webinar focused on reverse flow, you can certainly do that. And then if you're interested in looking at check valve SLAM in more detail, again, look for check before you wreck transient check valve modeling. If you want to learn more, again, this is part 3 of our 4-part series. Feel free to register for the reverse flow webinar, which will be happening next month. Or if you're from the future and you're watching our recordings already, take a look around our YouTube channel. There's plenty of good content there as well. A lot of good content today. I'd like to thank everyone that has made it through this point. I know an hour of engineering time can be pretty expensive, but hopefully it's valuable and it provided some new insight in terms of how to analyze these types of systems, especially if you're brand new to transient analysis. Hopefully knowing what to look for, where to look for it is very helpful. Of course, if you have any other questions, feel free to email them to webinars@aft.com. We'll do their best to answer them. And with the turn of the new year, we are looking for webinar topics for the upcoming schedule. So if you have an idea for a topic, whether that's a specific industry, specific application, the type of analysis, feel free to submit a topic to webinars@aft.com. Again, I want to thank everyone for attending, especially if you've made it to this point, and we look forward to having you in another Applied Flow Technology webinar in the near future. Thanks again.